everybody, and welcome to one of our Postdoc seminars. Of course, not given by a postdoc, but given by one of our visitors, Martin Mohlenkamp, who is going to talk to us about the curse of dimensionality. So I've been trying to say something about each speaker, and I was going to talk about the expertise of our children, but instead I think I'll just say that you've been very fun to have at lunch, and I think that you explain things in a really engaging and interesting way. I'm looking forward to your talk very much, and I think we all are. Thanks.
Good afternoon. Good afternoon. So, yeah, I do talks a little differently than some other people. So I've got goals and not goals. And they're kind of in pairs. So one goal is to show you a tool that you might find useful. And the tool, and I'll talk about various aspects of the tool. But again, the hope is that you find it useful. And the counter goal is that I'm not going to try to compare it with all the other methods in the world and show that it's better than them. And I won't claim that it's always better than them. It's going to be up to you to think about, oh, can I use this tool? Would it be useful to me? And then you can come talk with me and I can give you more details. And then, so there's kind of a central tool, and then there's going to be lots of little dead-end stubs where I'm going to say, oh, and you can also do this. And those are things that I've worked on over the years that I'm presenting them because you might find them useful for something. It'll make some of the talk a little scattered or disjointed because I'll say, oh, and there's this, and then there's this, and there's this. And the counterpoint to that is that I'm not really showing any results here to claim that what I've done is great. Mostly when I talk about my own work, I'm just going to whine at how long it took me to do it or how hard it was. But again, the point is the hope that you might think, oh, maybe I could use that for what I'm working on. You can talk to me. We could do some collaboration or something. Okay, so the fundamental problem is the curse of dimensionality. And here's the discrete version. That, okay, a one-dimensional discrete object is a vector. It costs some amount to store the number of entries. Two-dimensional objects, the corresponding object, we call it a matrix, and it costs the product of the one-dimensional costs to store. Three-dimensional is a tensor, and it's the product of the three one-dimensional costs. Anything bigger than that, we also call a tensor. And its cost is growing exponentially in the dimension. And from these pictures, you can say, well, yeah, that's how many things you got in it. And if you're going to do anything with it, it's also going to be exponential in the dimension. That's sad. Exponential in the dimension gets big really fast. Let's see, 10 to the 80 is the estimated number of particles in the universe. It ain't hard to get there if you're taking 100 to 1,000. It'll overwhelm anything. For functions, the corresponding statement, loosely, is that if you've got a function of d variables, maybe it's got some nice properties like smoothness, over p. You want to approximate it to some accuracy epsilon. Then the cost to store it, whatever you're going to do with it, is a cost to the power d. And the smoothness can help you in that constant, in the dollar sign there, but can't help you with the power d. And this is why it's a curse. It's unavoidable for any kind of a general smoothness class. Derivatives, mixed derivatives, that kind of stuff. If you encounter a method that seems to avoid it, which I have on occasion, these are the three things to look for. One is the constants in the method actually grow with the dimension. They're often hidden. You say it's big O of something. There's a constant in there, and if you work hard enough, you can see it grows with the dimension. The second thing I've seen is arguments that are inductive in the dimension. And if you track them down, it says, well, that okay, the rate might be better later, but to get to the asymptotics, you need d factorial things first. And then you can get to some methods. So d factorial is even worse than 2 to the d. And the third thing, which is the trickiest one, is you have some assumption, some bound on something in your estimates, that if you track that down with dimensions, it's actually implying that the set of functions this applies to vanishes, or becomes only the constant function. But these are ways that I've seen all three of these ways hidden in methods that seem to avoid the curse of dimensionality. And now here's your exercise, as mostly statisticians. So tonight, think about how these apply to your favorite Monte Carlo. Where is it cheating? You're used to saying error is like 1 over square root of the number of samples. Fine. But there's other stuff involved that has that curse. And I guess you can email me your completed assignment. Okay. So we've got this curse. You can't avoid it for anything general. Growing exponentially is very bad. So there's a philosophy on what do you do? You can't just give up. So the first part of the philosophy is that we can't deal with general functions, but we shouldn't want to deal with general functions because things that actually happen are not general functions. Things that happen in the world, things that happen in physics, are not arbitrary functions in the smooth class. And if your method can match somehow what's actually happening in your application or case, then you can avoid the curse. And this is pure philosophy. If the good thing happens, we can do good things. There's been a lot of work trying to characterize for a given method, well, what class of functions will it work on? And I've basically seen two versions, one of which is trivial. Oh, it's a function of d variables, but it only depends on 3 of them. Well, yeah, okay, then there's not the curse of dimensionality. So those are a trivial characterization. My method will work. Then there's circular characterizations. If the function looks exactly like my method represents, then my method will work. And there's various levels of obfuscation hiding that that's what's happening, but it really boils down to that. Maybe there's some way to do something better than that, but I don't know of any that aren't either sort of trivial or circular. All right, so that's bad news again, but we're not going to give up. Instead, what we have to do is work from some sort of inspiration of what we think should work. And the example, neural networks that people seem to like, is inspired by the visual cortex of cats. Cats do see. It works. And it will inspire us to have a structure that we think will work on some good stuff. The method I'm going to talk about is really inspired by physics, partial differential equations, things like heat flow. That somehow works. The equations work out. Heat works, and it's not that complicated. But it is just an inspiration. Okay, so here's the fundamental object, which is replacing something like a donut. Is you have your high dimensional object, T, for target. It's so this is the discrete version for tensors. It has D indexes and some range. You're going to approximate this with another tensor of the form of a sum of products of one index objects. So here, if we stick in indexes, we have a number. This is a vector. We stick in an index, we have a number. We take a product of some of those, we take the sum of some of those, we've got a number. It's inspired by separation of variables in things like the heat equation. Indexes are ugly. We don't want to use indexes, so T is approximated by G, which is a sum of separable things. Each of those is a product. Here we're writing tensor product. All this means is we have a vector and another vector. If you write them just next to each other, people think,
Well, the standard notation is that means matrix vector product, but that's not what you mean. You mean just set them next to each other and don't do it.
Then if you plug in an index,
Then you have numbers you multiply. But otherwise, you just hold it until you're ready to plug it.
okay. Now this object,
How much does it cost to store that?
well, you've got R things times D things.
Times a one-dimensional cost. So it's R times D times one-dimensional cost.
So now you're only linear.
In the dimension. Okay, so now we do the quiz. So where is the problem? I just told you you can't avoid the curse of dimensionality. So where is it hidden in here?
R needs to be.
An R. For an arbitrary function, R can be arbitrarily large. But for things that it works on, nice circular logic, and that have R small, it works. So circular logic again, but that's all we do. All right, so that's the tensor version, discrete. If you want to do functions, all you have to do is change notation. Change J's to X's and use lowercase letters, and it's the same. And this is something I've been fighting in my community about. There's the tensor people, there's the function people. It's the same, I shouldn't curse on camera, thing, just with different letters. Okay. It's a universal approximator in the sense that R is big enough, you can approximate anything. This is basically just the definition of measurable functions in R2 or whatever. Kind of a trivial thing. So this is the object. That is a feasible, for some functions, way to represent functions in high dimensions. It was developed not so much to represent a function, but to be able to compute the functions. So, we want to say solve a differential equation in 60 variables. Well, you don't just write down the solution, you have some process to generate a solution. So our basic paradigm for that kind of problem is you need to start with your operators, which is discretely as a matrix, or your functions, discretely as a vector, that have this nice form, sum of separable functions, or sum of separable operators. Then you do whatever your operation is that you do in one dimension to solve this equation. So something like iteration. So the simple steps are linear algebra steps. So for example, you might take your function, apply an operator to it. The operator is a sum of R things. There's the one-dimensional operators. And the function is a sum of R1 things. There's the one-dimensional functions. And you distribute through your sums, and it becomes a double sum of one-dimensional operator function applications, or say regular matrix vector applications. So our cost to do that is the product of the two ranks, linear in dimension. And then there's the cost of whatever it takes you to do a one-dimensional operation. So it's easy. We do that. Then what you see is now we've got a double sum, so we've really got R times R1 terms. If we kept doing that, that would grow. So we need a step where we take the results of this, try to squash down the total number of terms so that we can keep going. So algorithmically, you can run this. You can compute these things, compute in high dimensions. And our example, all right, so Radius statistician is not numerical analysis. Who knows what the power method is? Ooh, it is a different community. Okay, you have a matrix, you want to know the eigenvector with largest eigenvalue. That's good? Okay, so the simplest method to do it is you take a random vector, you apply the matrix to it, then you apply it again, you apply it again, you apply it again. And you normalize so you don't go to infinity or 0. And this will eventually converge to the largest eigenvalue. Because it's got the vector with largest eigenvalue. Because that one is amplified more than anybody else, So whipple done.
Okay, so if we have,
You know what Laplacian is? Laplacian? Okay, so say you have a discrete version of Laplacian, and you want the largest eigenvector, so an operator in eigenvectors, and a function. You can apply the operator to functions, like I did on the previous slide, so the multiplication kind of thing. Now you have more terms. Then you have a reduction step. You've got a new thing, new function, and you're going to apply this again iteratively. All right, so that's an example of the paradigm. Then, okay, so multiply is really easy. Reduce is the harder step. All right, so what do we want to do in that reduction step? We have a sum of products with more terms than we would like, and we're trying to fit it by something of the same form with fewer terms. We would like it to be optimal, but for now we'll just say small. Okay, so that's an approximation problem. Unfortunately, it is an NP-hard problem. We're not polynomial for any kind of exact solution. So what do you do for NP problems? You try some sort of optimization. So think of your neural network learning. So we have some initial guess for G. We're going to iteratively modify it to reduce an error. You might find local minimum and all sorts of terrible things like that happen, which will not worry about now. So you can try any of your favorite optimization methods. Variance newton's method, gradient-based, generalized minimal residual, something I don't know what that stands for. You can try all these methods. Generally speaking, general methods will choke on this problem. Sometimes, I contradict myself. For easy problems, all of the methods will work fine, but for more difficult cases of this, general methods generally choke. And then there's especially modifications people do. But there's one method that kind of is distinguished here, and it's using the particular structure of our functions. We have a multilinear structure. If you think of the vectors in one direction, which was the I index, if you fix just an I, this is a linear representation in terms of the function of one I. Multilinear. So we can use that. And the way you can use that is you have some sort of outer loop, then you have an inner loop through the directions or the dimension. And then you fix all your functions in the other directions. Solve for functions in your current direction. This becomes a linear least squares problem. And linear least squares problems you can solve with linear algebra. You can exactly solve these little problems, and looping them together, you get an overall optimization. Okay, so the equations you have to solve for the linear subproblem look like this, and the only real point here is with this is inner product of one-dimensional functions or inner product of vectors. That's a cheap operation and a product. These are all one-dimensional operations.
Would the rate of convergence depend in any way on the looping through the directions? That maybe some directions will help more than others?
It could, and there are greedy versions of this, and there are random versions of this.
Okay, thank you.
Okay, so these are one-dimensional inner products. Those are fine. Products. This is a matrix full of numbers. These are functions, or think vectors. So it's a vector of functions that you're looking for. Over here, these are numbers. This is a function from your target. So we're taking linear combination. So this is a function. So we have a vector of functions.
matrix of numbers times vector of functions equals vector of functions. That's okay, that's a worst case, think about converting the matrix. You can solve this. Okay, so you can exactly solve these subproblems, which is a lot more efficient than just following gradients. Okay, so this method is old, maybe 50 years. Very simple method to write down. It's stepwise robust, meaning you're solving these linear least squares problems. You can do that robustly. It's adaptable. A lot of the stuff I'm going to talk about is extensions work using this algorithm. It's widely used for these reasons. It doesn't make the overall underlying optimization problem easier. It just, I think I did say this. I've worked for years on challenges with this optimization. It's still a hard problem, and funny things happen, which I'm not really going to tell you about today. But here's a basic algorithm to try to solve this optimization. Okay. So, basic format, basic reproduction, and then you try to apply it to something, and you find out, oh, well, that doesn't quite work. So I spent 10 years working in quantum mechanics, trying to extend this stuff to quantum mechanics, because there are various complications to use. So I'm going to just hint at several of these extensions, not because I think you want to do quantum mechanics, but because you might see some parallels with something you do want. And it just generally shows that you can extend the. Okay, so one thing you can extend is by symmetries. In quantum mechanics, multiparticle Schrodinger equation, electrons have they're antisymmetric, which means if you exchange two variables, okay, so probably don't know any quantum mechanics. Who knows quantum mechanics? Okay, the multiparticle Schrodinger equation is the basic equation for electrons in quantum mechanics. It has this property that if you add another electron to the system, you don't just add an independent object, but you extend the dimensionality of the equation. So you add physical space, three-dimensional variable, every time you add an electron. So if we have a problem with 12 electrons, it's a PDE in 36-dimensional space. And you're solving for a single wave function that represents all 12 electrons. And this wave function has the property that if you exchange two variables in the wave function, you get the negative of what you had before. So it's anti-symmetric. And they have to be that way. If you're going to solve the equation, you have to get a solution with that constraint. Otherwise, it's not an electron. So that antisymmetry corresponds to an operator called the antisymmetrizer that enforces that. If you apply that to a product of functions, it gives you a determinant of functions. If you think about this, well, what would happen if I change gamma 1 and gamma 2? I can get back to my original by switching columns, and in a determinant that gives us a negative sign. This thing is, if you try to expand this out and represent this as functions, this has got factorial number of functions in it. You can't write it as a sum of separables. You get a factorial rank. But over here, it's a great object. And when you're going to do stuff with this, the main thing, well, one thing you need to do is inner products. If what you need to do is an inner product with these things, in a product of two antisymmetric things, you can compute as a determinant of a matrix of numbers, and those numbers are just inner products of the orbital functions. Matrix of functions, you have to expand out and get factorial. Matrix of numbers, that's an n-cubed operation. So that's perfectly easy. So we've extended, we can handle antisymmetric functions. So that's extension to symmetries. Then you can hit times where your operator is known analytically, but is not representable as a sum of products. So the paradigm I described before, where you apply, get that, and reduce. You can't do it because you can't get that because you don't have smaller. But in the scheme, you don't actually need this middle step. What you need to be able to do is compute these inner products. Compute inner products with the middle step. And you can sometimes do that implicitly in the inner product. So here's the electron-electron interaction operator. So this says two electrons don't want to be at the same place at the same time. Or they want to be at the same place, they repulse each other. This thing, you can't write it separable in Ri versus Rj. But in the inner product, you can compute what this thing is. And the formula was too long to just put on a slide, so I suppose. Okay, but the moral is sometimes you can take an operator and you can implicitly represent it by figuring out how to compute with it. Another thing we found in quantum mechanics is there's two more reasons why this can't possibly work. One is that electrons, because of the interaction, they have a cusp in, as two electrons come together, it has a linear cusp, which is poorly represented as a sum of separables. Well, you can explicitly include extra linear cusps as a prefactor on a sum of separables, as long as you can figure out how to compute with it. And this was a big beast, but you can compute inner products with these objects. And then the last one, if you have a system of electrons and another one over here that don't really talk, and then more and more and more, if you try to represent that globally as one of these sum of separables, it scales exponentially in the number of subsystems. But if you use a recursive format, you're doing subsystems, and sums of products of those things, then the scaling will be okay, and you can compute. Okay. So now we can do a mini conclusion. So, this representation gives a tractable way to represent some set of functions of many variables. You can compute with them. You need to square your function. You need to do stuff with them. You can do it in this form. And I will should contrast it with like a neural net. And how do you solve a PDE with a neural net? It doesn't make sense. Well, these were designed for computing. And there are various extensions. And I gloss over the difficulties. This is probably a good place for preliminary questions.
What's the definition of black for ALS?
Let's see, it's cubic in the rank, linear in the dimension for a pass. What else do we need to know? Those are probably the main things.
Are there other algorithms for this?
There are. So, for example, people do Gauss-Newton. Plain Newton's method is too expensive. Gauss-Newton is okay. You can try a gradient descent kind of thing. And yeah, there's actually, because of the difficulty of the approximation problem, a lot of people have developed stuff. I haven't found any of it to be any better than ALS, but others would disagree.
Is there any sense in which sums of functions that are sums of separable functions form a mesh in some natural function space?
It forms a Segre variety.
Oh, fun.
I had to learn some algebraic geometry. So if you take like a fixed rank, sums of separable function with 5 terms, it forms this thing called a Segre variety in algebraic geometry stuff. I haven't found that really useful at all. There's people there that try to prove some abstract things about these objects. It's not a space. Or a fixed string is not a space.
I I'm wondering if it is in some sense well distributed through the set of functions, that I can probably find some function of that form that's close to any arbitrary function I choose.
If you fix the rank ahead of time, then it will be almost surely no.
Okay.
And part of that is if you say you take, say, tensors that are 100 on a side in dimension 50, the generic rank of a tensor is huge. And you take a smaller rank, and it can't be near those things.
Okay. Thank you.
In your algorithm, in the ALS function, do you have interpretations for the tolerances in terms of what's in your data, or they don't have the physical interpretation? Like, you know, like in linear regression, you can interpret when you have fixed effects and linear error terms. In the ALS, is there a way to think of what's happening in the algorithm in terms of what we're getting at?
I'm not sure this is quite your thinking. If you can think of, the way I think of it is it's an alternating orthogonal projection. That if you fix these, you're fixing most of the space and you're orthogonally projecting onto what you can represent in the other dimension. I think that's as good as I can imagine. Any other questions? Okay, so that was part one. Part two is on regression, machine learning kind of stuff. So, okay, so we have data. We're going to define an empirical inner product, just evaluating the data, which also allows you to do inner products of functions with data, and gives you your standard empirical squares of error. That's our general setup. Well, this is what gives you a way to represent a function of many variables. So we can construct something as a sum of separable functions to fit your data. And that's what a neural network does. Neural net does, right? So this is a kind of a different framework that in principle can do some kind of. You can use an ALS type approach to do the fitting. So you loop, you need to know what rank to choose, and there's some other kind of meta parameters that you might do. But within that, you loop to the dimensions, fix the functions and other variables, update the functions in their current variable, current direction to minimize error. So that's how the error is written down. So this is all the stuff in the other directions. These are the functions you're looking for. Okay. Right now, these are values of the function at points. We need to decide how to represent them as functions. If we chose them to be a linear combination of some basis functions, say you say, I'm going to do polynomials of degree up to 7, and you can write the coefficients with that, then it becomes a linearly squares problem in the coefficients, and you can solve it. If you don't choose that form, you can say, oh, I'm going to have rational functions with 6 parameters, and it's a nonlinear problem, but it's a smaller nonlinear problem. And the only thing here is that you can run the thing. You still have problems, standard psi techniques. The cost is linear in both the d and the n, so it's feasible. And this shows how dated I am. I have a paper on this from years ago. And as of 2009, on some benchmark tests that my co-author found, it was competitive, enough to be published. And then Joe Kinsgarka, who was co-author in 2010, did a classification paper with similar methods, and as of then it was competitive. I have no idea how this would compare with modern methods. I would not bet on it. But it's possible. Okay. And then, So that's a generic, another way you could do regression of any variables. And then an application I've worked on, which I'll tell you about just because it might be useful, and it might actually use it, we might actually use it in a novel applications work, is trying to regress on molecules or materials. So what your data looks like, okay, your y is the value of some function, and your sigma is a molecule. So it's specified as atoms at locations. Or possibly it's a material, which is atoms at locations and then it repeats periodically. And you want to regress on it. So an atom, let's see. Atom has two things. One, it has what it is. Physicist people, we were doing molybdenum and tantalum. Okay, so that's a categorical variable, right? Just the label, and then you've got positions in space. And you want to get that into your learning algorithm so you can learn this. And kind of an approach we figured out is, well, we've got an unordered list of, or set of atoms, and how to get that in there. Well, you can map that to a set. Each structure, a single one goes to a set. It's elements of two things, a weight, which total up to 1, and an ordered list of atoms in a particular kind of canonical order, such that if they gave you these in a different order, you get the same views. If the whole thing gets translated or rotated, you get the same views. So it makes it invariant under those operations, which is what you would want. Because your system of coordinates should not affect the property of the molecule. And this is kind of fun, so here's how you do it. So this is a fake structure, A, B, C, D. The lines are just for visualization. We've got 4 atoms. So we're first going to split into 4 group views, starting at A, B, C, D. And then from A, you say, well, what's the nearest atom to A? Well, it's C. So we're orienting A to C. Next nearest is B, which defines the y-axis. And the fourth one is D. And we terminate because it's fine. If you start at B, the nearest thing is C. And the next nearest is A. And if you reorient, so that's y-axis is along C, z-axis is along A. And then the most distance is D, which is if you start with C, then there's a tie on nearest. So it's split. The weight is split. And we can either follow the A path or the B path. And if you start at D, C is the next nearest, then D. So we have 5 views. The weight's under 1. They came from splitting.
Doesn't D also have a tie up between B and A?
No. C is
C is the closest, but then the next one after that is from D.
not in this example. Because of the Pythagorean theorem, the diagonal is shorter.
Ah, oh, okay, you don't have to follow the code. Okay, thank you.
She gets electric Okay, so there's a way of mapping to these weights, and then if you think of things in terms of these views with weights, then you can define a function of a structure as a weighted sum of functions on ordered lists of atoms. And ordered lists of atoms, we can do functions. So we can now try to minimize the distance from our data to this, what I call a consistent representation of G. So that's regular least squares error. And CG is given by the weight, the sum over the views of that structure with weights and a root function of a list, ordered list of atoms. Okay, so up to here, it didn't have anything to do with sums of separable functions. And in our working group, and everybody else here is doing that. One of them toxicity measures of various chemicals, and what to hear might possibly be this kind. Now, so we have a G is a function of a list of atoms. If we say, well, only for any given atom, only the 10 nearest ones are going to have an effect on that. Truncate that to a finite, and you can represent that as a sum of products of one atom. So that's where you're trying to get around the curse of dimensionality. A one atom function is a reasonable thing. So an atom has a species type and a position. So species type means you're really just going to have a separate function for each species. And then you have a function of 3D. You have to decide how you're going to parameterize a function. Probably spherical harmonics. Okay. So this is kind of extension of one of these that I know more about this if you're interested. So conclusions for the second part look a lot like the conclusions for the first part, but just the point that you can do regression, machine learning kind of things with these. Okay, questions on the second one?
Have you done any regression with molecules? I mean, what would be the typical response value?
So there was a paper with some physicists.
It was molybdenum tantalum alloys, and it was enthalpy, which I don't even understand what it is.
Okay.
And that's as far as I took it, and then my collaborators kind of bailed out, and I went and did other stuff. Yeah, which is kind of the main regression thing. It was like that too. It was a side project for me. I did that, and then I was busy doing quantum mechanics and stopped. And now I'm here. I'd like to see if it's viable or do something. See if it's viable. Other questions on part 2? All right. So part 3 is just a few examples of functions written as sums of separable functions, to just give you some flavor for what you see. And there's some morals along the way. Okay, so your favorite function as statisticians is probably the Gaussian, right? Well, it's 7. So it can be written as a rank 1 sum of separable functions. A more useful, well, that's useful in itself, but the extension of that is if you have some function of a positive variable that can be approximated as a sum of Gaussians, which is the kind of thing people have studied. Given a usually monotonic function or variable, how do you optimally represent it as a sum of Gaussians? Then you can represent the radial function based on that as a sum of Gaussian. You stick your variable in, and it separates. So the number of terms depends only on how well the radial part expanded with the Gaussians, and that gives you your rank for your sum of 7. And that statement there is independent of dimension, but I'll give you a caveat. You got to think about how you're approximating and what you're using it for. Now, this is not a general function, so it's okay to beat the curse of dimensionality, but you do have to be a little careful. It's useful in my kind of world for Green's functions. So 1 over distance is the Green's function for the Laplacian operator. So if you've got a distribution of particles, and you want to know the gravitational field, you apply, you convolve with that operator. To get the gravitational field. So it comes up in physics. So this is useful construction. So a linear model, which is what we keep seeing here. That's again. It's a similar kind of thing. If you can represent your basic function as a sum of exponentials, not Gaussian, plain exponentials, and you're sticking the combination of your variables plus b inside of it, then you can put in your expansion and write it as a sum of products using the separability of exponentials. And again, the number of terms r depends on your original function, not your dimension. So here, smoothness kind of properties of phi matter, and how good you can expand it. One world here is, once you have that expansion, the actual orientation of AI xi versus your axes doesn't matter. You would think with separable things that the axes matter. And here's at least one case where they don't matter. And the caveat is, well, if it happened to line up with exactly one of the axes, you just get one term and it would be great. But if you discount getting lucky, then the direction is. And then, let's see, Maggie here. Maggie.
Maggie's hungry.
Yeah, you were asking me about additive models. There's my slide about additive models. So if your function is a linear combination of functions of single variables, well, this is already a rank D representation. You're just product with one in all the other directions. But here's a weird thing that happens. You can write the sum of functions of one variable as the derivative of a product evaluated at 0. This is a big product rule. Differentiate one term, the t, you differentiate and you get your half I, and the other terms get t equals 0, and that closes that. Okay, so then a derivative is a limit. And you can do a derivative as a limit of two things. This is the center difference. And each of these is a product. If we fix a small h, then we have an approximation with two terms. So this is an object. Well, first, approximation with two terms, that's great. We only use two terms. This is an object you can prove that for general FIs, this requires d terms. But it can be arbitrarily well approximated with two terms. So one moral that's kind of sad is that means if we have this object and say, give me the best representation with two terms, this is an ill-posed optimization. There is no best approximation. It's an infimum. It's on the boundary of this space. That makes the optimization all hard. They don't like it. So that's the bad news. The good news is, well, we've got a darn good approximation with two terms. So this can actually be a good way to approximate things as derivatives of other things. Third issue, well, we're dividing by h, and we've got something that's positive and something that's negative. We have two really huge things of opposite signs, and we're canceling to get a medium-sized thing. That's kind of a bad idea numerically. So you can't push those two. And I guess I should have said fourth thing. Is this kind of a cool structure? I actually figured this out numerically. Okay, and this is an example. This is my favorite example. I've gotten much mileage out of it. I also figured this out numerically. Trigonometric identity. If you have the sign of the sum of d variables, you're going to write it as a sum of d things of this form. Maybe I should have put the 3 variable one just to show you. For any i's of the parameters, as long as you don't divide by 0. So this is a non-standard trig identity. If you take this and you use your ordinary trig identities, sine of a plus b, use that to expand into two terms, and that picked off x1, and then you do it again, that doubles your number of terms. You'll get 2 to the d terms. And this was one of those moments when I figured that out first and said, oh my gosh, we're dead. And then my collaborator said, well, try it. And then I got graphs and eventually figured out this one. Okay, so naively, you think about it, you say, this is terrible, you get 2 to the d terms. Actually, you can do it in d terms. That's one rule. So non-obvious things happen. All of the complex numbers you can do with 2 terms. So this is a well-known thing, that the field you're doing expansions over matters in ways that it doesn't for matrices. The rank of a matrix is the same over R and over C. The tensor rank, more than 2 directions, is not the same over R and over C. This thing is not even vaguely unique. You've got parameters, you can vary them all over the place, and you still have equality. So these things can be highly non-unique. The counterpoint is lots of people have worked to say, generically, a tensor, if you have a tensor and it has some low-rank form, then generically it is unique. And that's not true for matrices. So you have more uniqueness in higher dimensions, in general, generically. Yet, there's pretty simple examples where you don't have uniqueness. It's kind of fun. And there's arguments of whether uniqueness is good or bad. People are trying to analyze what you get out, interpret it with like a uniqueness. People are just trying to approximate and say, well, I don't care which one I got. Having more of them is good. Okay, and then if you have a sum of products, you might think, well, let's choose my functions to be from some set I like, some basis set or something. Or let's make them orthogonal because we like orthogonal things that'll be convenient. Those are terrible ideas in this context. Orthogonality is your enemy. And this is an example to illustrate. So here's a function that I've written as a sum of 2 products. First one is a product of orthogonal functions with 2 variables. The second one, I have my original set and then a shifted set. And I've got 2D orthogonal things. So everybody's orthogonal to everybody. As I started, this function, gi, or say g1, is not orthogonal to g1 plus gg plus 1. So I don't have orthogonality here. To enforce orthogonality, I say, I want this same function, but with an orthogonal expansion, you have to expand it. So my g1 and my g1 plus d go on different terms, and then this part's duplicated, and then and then you say, well, in the 2 direction, this is still not orthogonal to that one, so I have to expand that and double again. And you end up with 2 to the d terms. So the cost for getting orthogonality is exponential. Don't do it. Everything you learned about linear algebra for 2 dimensions doesn't work for 3 dimensions. Don't do it. Okay, so there's no theorems that says any of this works. There's really no theorem to say anything in high dimension works. But there are intriguing examples, and there's experience by myself and lots of people that at least sometimes work. If you actually want to compute in high dimensions, there's really there's not much competition. Things that can be computed in high dimensions and scale okay, even just on a restricted classes. So that's one reason I kept pursuing this. Is like, well, what else am I going to do? What else can I do? There are alternative tensor formats that have been developed. So there aren't just sums of separables. There's some tree versions, and there's product, recursive product kind of versions. Let's see, there's a bunch of stuff on my website. And again, this was trying to plant seeds, give you possible tools. I'd love to talk with people about them in detail. Thank you.
This is fascinating. Do you have have any strategies for how one could sort of compare your method? Well, you mentioned the bake-off that you did with classification and regression for one of these. Would it make sense for your working group to try it on comparing some of the more modern techniques against the UCI repository or something?
So the more I think about it, I don't see how this could like beat neural networks. Deep neural networks. What I am getting the subgroup, my working group to do is see if there are hybrids. See if there's some functions that deep neural networks don't do well and this would do well. And then are there ways to combine the techniques?
And that gets back to a bake-off thing where we have to compare deep neural networks and your methods with a family of a set of functions.
Yeah, so for the simplest example, I think of x1 times x2. You know, a neural network can do it, but it's doing piecewise linear, blah, blah, blah. It's taking a lot of effort. And it's trivial here. So can you find a way to utilize the power, stick some of the power of this in the right places in the net so that it can save that x1, x2?
Do you know any specific applications of this technique? And also, maybe you know some review papers that are relevant?
For learning or for quantum mechanics or
Like learning in general.
I guess first I suggest go here and read the original papers. So it hasn't really been pursued much since I stopped doing it. Not much.
But I don't. The methods are all over, but there are like I know there are new people who are constantly trying to use them. So it's not necessarily something worth pursuing your group.
So, well, I think we need to talk about this. I haven't done machine learning until 3 months ago, or in the last 10 years. So I'm not up to speed at all. But we should talk about it.
No question about the ALL. So go back to your slide, the ALL. Yeah, for this one, for each iteration, how do you ensure that you still have a rank R or almost rank R the data class such that your first matrix is not ill condition?
Okay, so the keeping of rank R, this is the description for R is already fixed.
Yeah, R is fixed, but the function, your function space can be less than R could that be less than R?
So if the true thing is less rank than what you've put here, generally you won't notice it and you'll just get whatever rank you put in. And part of that is it really has no incentive to use less terms than you give it. In terms of conditioning, in principle this could be unconditioned, but if you think about it in terms of orthogonal projections, the projection is well defined, no matter what. So, for example, if you use an SVD to solve the equation, or you just use the nearest point to where you were, it's just as good a solution as any.
Okay. My second question is that instead of using d-dimensional tensor per DAG, I think it would be useful to think, for example, we start with one variable tensor and two variable tensor and so on and so forth, such that this model would include the additive model. So you do not need to write the additive model into a full D tensor structure.
Okay, so the additive model was, I presented it just as an example of how the structure would be. If you know you've got an additive model, you just use that. Within this thing, I could assume, so I get to have a choice here somewhere. I mean, so here your functions you get out are determined by the function you put in. For the regression problem, you to define the spaces in which each of your things live in. And you can just say, well, this one lives in the space of constants. And kind of null out some of the variables. And that's equivalent to not using some of the variables. But you can use it within the same structure just by putting some of the spaces to just be constants.
My third question, sorry, I have so many questions. Yeah, my third question is that I think for the function, in terms of functional approximation, I think the method would work for tensor space. I think that we have some theorems for that. Or maybe I think something else.
Well, if you think it beats the curse of dimensionality, then you're thinking something. There's a this. These comments are based on a nice, very well published proof that in a certain space, and I don't remember doing the
Tensor
tensors.
space. So that it can be tensor each dimension. So it's smaller than general survey space.
Yeah, I think it might even be that one. I have to check, but
Yeah, but generally it doesn't.
well, okay. There's a proof that this kind of thing actually works for some space, and I remember the space was. And it's the proof. Every step in the proof is correct. I can verify it. But it has a hidden constant that grows exponentially. It has an inductive thing that puts a d factorial in it. And I think it doesn't have a third one. So I would worry about whichever thing you're referring to. But actually, there's something wrong with it. There's the no free lunch. But